All right, welcome to section 2.6, limits at infinity and horizontal asymptotes. All right, so in this section we let x become arbitrarily large, positive or negative. In other words, x is going to go to infinity, right? And we're going to see what happens to y, what's going to happen to our function. All right, so let's begin by investigating the behavior of the function f, defined by this one right here. F of x is x squared minus 1 over x squared plus 1 as x becomes large. So the table gives values of this function correct to 6 decimal places, and the graph of f has been drawn by a computer. So you can see what's happening, right? So plus or minus, we're going to make these x values larger and larger and larger, right, as x becomes large. So 1, 2, 3, 4, 5, 10, 50, 100, 1,000, and we see what's happening with our y values. Well, as we make x really big, it definitely seems like we're approaching 1, right? It just seems like the more zeros that we put on the x, the more 9s we're going to get after the decimal here, right? So that kind of insinuates that the limit is going to be 1. And we can see that right here on the graph, right? So if you remember, this horizontal line y equals 1 for this particular graph is what's known as an asymptote. All right, as x grows larger and larger, you can see that the values of f of x get closer and closer to 1. In fact, it seems that we can make the values of f of x as close as we like to 1 by taking x sufficiently large. All right, so this situation is expressed symbolically. So now we're going to take the limit, right here, the limit as x approaches infinity of this function here equals 1. All right, in general, we use the notation, again, it's what I just said, right? Limit as x approaches infinity of the function equals the limiting value. Okay? To indicate the values of f of x approach L as x becomes larger and larger. All right, so here's the intuitive definition of a limit at infinity. So let f be a function defined on some interval from a to infinity. So this is an open interval. Then let limit as x approaches infinity of f of x equal L means that the values of f of x can be made arbitrarily close to that limiting value by requiring x to be sufficiently large. In other words, x goes to infinity. Okay? This is an alternate notation here, but this is the one you're going to see the most often. All right, so here's just some different geometric illustrations of asymptotes, right, of this situation with the limits at infinity. So as these x values go on and on forever, we can see this graph is definitely approaching but not crossing y equals L. Very similar with this graph here. A little bit weird with this graph here, right? Normally, what we're used to is a definition of an asymptote being a line that you don't cross, right? It gets closer and closer but does not cross. The but does not cross part doesn't always necessarily hold true. This red line here, this pink line, is still an asymptote, right? And you can see that this function oscillates above and below this y equals L line, this asymptote. It's going to get closer and closer. It's still, it's going to keep on going forever and ever like that. It's my drawing, but get closer and closer, but it's still going to keep going above and below that asymptote forever. Notice that there's many ways for the graph of f to approach the line y equals L, which is called a horizontal asymptote, as we look to the far right of each graph. Referring back to figure 1, we see that for numerically large negative values of x, the values of f of x are still close to 1. In other words, as we approach negative infinity, as x approaches negative infinity, in this particular case, now don't assume this is always true, but in this particular case, the limit as x approaches negative infinity for the same function is the same value of 1. Okay, but don't assume that for every function. So this is just saying we can do the same thing in the negative direction. All right, definition 2 is illustrated below. Again, just same thing. We're taking these x values to negative infinity and seeing what happens to the function. Definition 3, very important. The line y equals L is called a horizontal asymptote of the curve y equals f of x if either, so notice the wording here, either So either one of these things can be true. Only one needs to be true, and you've got an asymptote, horizontal asymptote. So as limit as x approaches infinity of the function equals L, or the limit as x approaches negative infinity of your function equals that limiting value. Okay? All right. So let's find some limits at infinity. So here we go. The limit as x approaches infinity of 1 over x equals, well, remember we're used to, I keep telling you, ask yourself the two questions, right? Is our function a polynomial or rational? This one's rational. But then we say, well, is a in the domain? Well, a in this case is infinity. All right, so we can't really plug in infinity. If you could see me now, I'm doing air quotes, plug in infinity. So we're going to kind of fake it, right? We're going to fake plug in infinity, but we're going to just think, right? Not even going to graph it. We're going to think here. We're going to analyze. So what happens to 1 over x as x gets incredibly huge, right? So we kind of talked about this in the last section, but kind of going the other way, but still. As the fraction gets as the denominator gets incredibly large, what happens to your fraction? Well, let's analyze it. So let's see, 1/2, let's make the denominator bigger. 1/3, denominator bigger, 1/4, 1/5, 1/10, right? Whatever, how many zeros that is, right? What's happening to that fraction? It's getting incredibly small. Actually, since that denominator is going to infinity, the denominator is getting infinitely large. That means the fraction gets infinitely small. In other words, our limit goes to 0. Okay? So that's important there. All right, so let's try the other one, the limit as x approaches negative infinity of 1 over x. Well, actually, it's the same logic, isn't it? Right? Just put a bunch of negatives on these things. Well, it doesn't matter. They're still incredibly small fractions, right? As the denominator gets infinitely large negative, the fraction still gets infinitely small, right? So still approaches 0. Okay? Those are important concepts to understand. Very, very important concepts to understand. Okay? So we have a theorem here. If r greater than 0 is a rational number, then the limit as x approaches infinity of 1 over x to the r power equals 0, right? And that's the same logic we just used. I mean, if 1 over x, the limit as x approaches infinity of 1 over x equals 0, well, if you take that denominator that's getting infinitely small and take it to an exponent, it's still going to be incredibly small, right? So that's the logic there. So it's still going to approach 0, and same with negative infinity. Okay? All right, very important. Also, this is important. All right, so in this chapter, we're going to learn all kinds of different ways to manipulate these functions to be able to calculate limits. Okay, so here we go. Evaluate the limit as x approaches infinity of that big old mess and indicate which properties of limits are used at each stage. So what we could do is we could do this the really, really hard way and break it into little pieces and then all this. I mean, it's going to be a big pain, to be honest with you, but we got a little shortcut for you. So whenever you have something like this, a fraction like this, all right, and we're trying to take the limit as x approaches infinity. Now, this only works for infinity, or negative infinity, of course. What we're going to do is we're going to identify the variable in the denominator with the largest exponent. Okay, in this case, x squared. All right, so again, the variable in the denominator with the largest exponent. We're going to take that variable with the largest exponent, in this case x squared, and we're going to divide every term in this entire fraction, top and bottom. Oops, kind of made a mistake there. There's a term. Remember, terms are separated by addition and subtraction. We're going to divide every single term by that x squared, okay? By the variable with the largest exponent in the denominator. So we've got the limit as x approaches infinity. And I'm going to write it like this. 3x squared minus x minus 2. I'm going to give myself some room here. 5x squared plus 4x plus 1. It's kind of hard to see. There we go. All right, and then like I said, we're going to divide each of these terms. Again, terms are separated by addition and subtraction in math. Okay. Then we're going to simplify. So the limit as x approaches infinity. Remember, you've got to keep writing that. Limit as x approaches whatever. Limit as x approaches whatever. Every step until you substitute. Okay? All right, so let's simplify. 3x squared over x squared is a plain old 3. Negative x over x squared is negative 1 over x. And we'll keep going. Negative 2 over x squared. 5 plus 4 over x squared plus 1 over x squared. Okay. So you're looking at it and going, wait a minute, did that make things easier? I promise it does. Hold on. Because watch this. We remember that in this case, and I'm not going to write it all out, and you don't have to write it out broken up in pieces. Remember, we can take the limit of each of these individual terms and then add them, subtract them, divide them, etc. Right? But let's kind of just do it all in one piece. So what's the limit as x approaches infinity of the constant function 3? If you remember, it's a horizontal line at 3, right, at y equals 3. So no matter what the x value is, the limit will be 3. All right? Now, 1 over x, we just covered this, right? Limit as x approaches infinity, our denominator is getting infinitely large. So the fraction's getting infinitely small, which means it's going to go to 0. So this is just kind of, showing your work notation, an arrow through it like that, pointing to the 0, means that fraction goes to 0 as we apply the limit. All right, and then we just had that rule up above, right? 1 over x to any exponent, right? As long as it's a positive exponent. This will also go to 0, right? Because if x is going to 0, well, something incredibly close to 0 squared is still something incredibly close to 0. Okay? All right. And then, so those are all zeros. Limit as x approaches infinity of the constant function 5 is 5. And then applying, I think I made an error there, didn't I? There we go. That should just be a plain old x, yeah. All right. Anyway, so 4 over x, as x gets incredibly large, this goes to 0. Same thing for 1 over x squared. So there we go. That's the answer. Okay? And when you do a problem like this on the exam, you do need to show work. You cannot show just a simple answer like this and expect full credit. Actually, if you only show the answer without any of this supporting work, you'll only get 1 point out of however many, probably 5 or 10 points that the question's worth. So please, please, please make sure always show your work. This is calculus now. Time to show your work. All right. All right, here's another one. So let's see. Find the horizontal and vertical asymptotes of the graph of this crazy messy function here. What a mess, right? Okay, so horizontal asymptotes, what we're going to do is what we just did, right? Remember, we're going to take the limit as x approaches infinity, see if we have some limiting value, and that limiting value will be the horizontal asymptote. So let's work on that first. So we're going to have to use that trick we just did. Oops. All right, so limit as x approaches infinity. Now I'm going to give myself some room here. All right, this is radical 2x squared plus 1. Give myself some room because we're going to end up dividing here. 3x minus 5. Remember the rule. Again, we're going to find the variable in the denominator with the highest exponent. Okay, it has to be the denominator. In this case, it's just plain old x, right? So we're going to divide everything by x. Now notice how I wrote the numerator different than the denominator here. You'll see why in a minute. All All right, so let's do, so we've got, again, keep our limit notation going. Limit as x approaches infinity. I'm going to hold off on writing that numerator for a second here. I'm just going to clean up this denominator. Okay. Okay. We want to divide this radical by x. That's kind of a pain. We really can't. Now, be careful, be careful, be careful. You cannot break this up like this, right? Because the entire numerator is under a radical. We cannot break it up with the addition and subtraction. What we've got to do is actually we have to use this rule here that you remember from algebra and geometry, right? So if you have the square root of a over b, a over b, that can be rewritten as square root of a over square root of b, right? Or vice versa. We can go left to right, right to left on this one. So what we have to do is we want to end up dividing each of those terms inside the radical by x. But the problem is if we put x under this radical, it's no longer x. Okay? Let me show you what I mean. In other words, it's going to be an x squared under the radical. Okay? Because of this rule right here, right? So this would end up, if we broke it up like this, be radical 2x squared plus 1 over radical x squared, which is radical 2x squared plus 1 over x, which is what we got right there, right? So you guys see what I'm doing? I'm putting this x under the radical. When I do that, it becomes an x squared. Okay, that's important. That's an important little trick here, manipulation, algebraic manipulation. So we'll do it like this: square root 2x squared over x squared plus 1 over x squared. Okay, still gonna clean this a little bit. So equals, again, limit notation. This is going to be square root of 2 plus 1 over x squared, all under the radical, 3 minus 5 over x. All right, now we can apply the limit as x approaches infinity, right? So this will be, so let's do it piece by piece here. So look, this will go to 0, right? Denominator's getting huge. See, oh man, it always does that. There we go. 5 over x also goes to 0 as we apply the limit as x approaches infinity. So all that's left over is radical 2. Actually, I am going to save myself some room right here. Radical 2 over 3. So there we go. Thus, y equals rad 2 over 3, that was a bad 3, so 3 is a horizontal asymptote. I don't want to write horizontal asymptote out. You don't either. You can write HA for horizontal asymptote. Okay? There we go. Because we followed that rule. We took the limit as x approaches infinity of this function. We got a limiting value, so that makes it a horizontal asymptote. Okay. All right, so now vertical asymptotes. We talked about this a couple sections ago. So these are horizontal, so let's do vertical asymptotes. All right, to do that, we have to look at the fraction, right? We're dealing with a fraction up here. We're going to find, we can actually find this algebraically, but we need to prove it with calculus. We know that the undefined, or the limits to the domain of this fraction are, we take the denominator set equal to 0. You guys can do this, right? This is 5/3. So the domain is all real numbers except for 5/3 in this case. So what we need to do to prove it with calculus, and you must prove it with calculus to get credit, is we do the limit as x approaches 5/3 from the left, radical 2x squared plus 1 over 3x minus, I cannot write, minus 5. Okay, so we have to analyze this because it's not necessarily that easy to just look at and do, right? Plugging in, we can't plug in, right? Because we do have a rational function, but 5/3 is not in the domain. Okay? All right, so let's look at the numerator. Let's analyze the numerator here as x approaches 5/3 from the left. Okay, so just think of a number line. 5/3 from the left. 5/3 is what, 1 2/3. It doesn't really do anything. We're gonna square it, we're gonna double it, we're gonna add 1 to it, and we're gonna square root it. The numerator's, no matter what, is gonna be a positive value, right? So the numerator is going to be a positive value. All right, let's analyze the denominator though. The denominator, let's see. If we plug in 5/3, we get a 0, right? But just think, if we come towards 5/3 from the left, okay, so that's going to be less than 5/3. So just think like, plug in like 5/4. I'm sorry, 4/3. My mistake. Plug in 4/3, right? That's going to give us a negative number, right? Because it's going to be less than 5, and we're subtracting 5, so we'll get a negative number. So the denominator is going to be negative. But what else is going to happen to that denominator? It's going to be a negative value, but it's going to be incredibly close. This part's going to be incredibly close to 5, right? We're getting there. So 5 minus 5 would be 0. So this is getting, or approaching, 0. Okay? So if our numerator is positive and our denominator is negative, that means the whole limit's going to be negative, but the denominator is approaching 0. And remember last section we talked about that. If the denominator gets incredibly small, the entire fraction gets incredibly large. Okay? So we have a negative large number, in other words, negative infinity. Okay? Okay, I know that's tough, so go through that, analyze that. Just to show, now we've already shown there's a vertical asymptote here at 5/3, but we're going to show from the other direction as well. Limit as x approaches 5/3 from the right. Okay, it's going to be the same logic, right? If we plug in 5/3 from numbers above 5/3 but approaching it, our numerator is still going to be positive. If we plug in numbers that are bigger than 5/3 though into the denominator, it's still going to approach 0, right? The whole denominator, right? It's still going to approach 0, but it's going to be positive as well this time, because we're going to have this term, with this term getting close to 5/3 from the right, is going to be bigger than 5. So something bigger than 5 minus 5 is a positive value. Okay, so positive over positive, denominator is approaching 0, so the denominator gets incredibly small, the fraction gets incredibly large. Okay, all right, and thus we have a vertical asymptote at x equals 5/3. Okay, so that's the work you've got to do to prove this stuff. Again, it's very important in this chapter, in this class, to show your work to get full credit. Okay, all right, so now what we can have is infinite limits at infinity. In other words, we could take the limit as x approaches infinity of a function, and the function can just get huge forever, right? And of course, we could have any combination of that. We can approach negative infinity and get positive infinity. We could approach positive infinity, get negative infinity, or negative infinity and negative infinity. Any of these combinations, any of these four are possible. Okay? All right. Let's keep moving here. So example 4, compute this limit. All right. Well, we have a problem here, right? Well, we will. Let's try this out first. All right, so we're gonna, and I'm air quoting right now, you just can't see me, but air quotes, we're gonna plug in infinity here and here and see what happens, okay? Again, air quotes, you cannot plug in infinity. Infinity is not an actual number, it's a concept. But we're gonna plug in, air quotes, plug in infinity here and here. Well, if we make x incredibly large, and you square it, and you add 1, and then you square root it, it's still incredibly large, isn't it? Say yes. Yep. So we'll get infinity on that part. Minus, well, if x goes to infinity, then x goes to infinity. So you might ask yourself, well, or say to yourself, hey, infinity minus infinity, isn't that 0? No, unfortunately, it's not. Okay, so infinity is a concept. It is not a specific value. So just because one set is infinitely large and another set is infinitely large does not mean they have the same number of items in their sets. So infinity minus infinity, you can't do that. Okay? So whenever you do this, you're doing a problem and you get infinity minus infinity, go, okay, something's wrong. I need to use another method here. Okay? Now that method is this, watch. So limit as x approaches infinity of this big old mess here, oops, x squared plus 1 minus x. Now, if you remember something called multiplying by the conjugate, hopefully you do remember, because it's an important concept. The conjugate means you take what you've got and just change the sign in between. That's it. Okay, so in other words, we're going to multiply top and bottom, right, by that. Okay, because this is 1. Anything over itself is 1. We're allowed to do that. Oh, and I did not use my parentheses properly. I need to do that. There we go. Okay. All right. So, on top, in the numerator here, you need to FOIL. Okay, first, outside, inside, last. So here's first, outside, inside, and last. When you do that, but actually you don't even have to FOIL, right? Because multiplying by the conjugate automatically sets up a difference of squares for you. So really all you have to do is first times first and last times last with a minus sign in the middle. It's a difference of squares. Okay, so we're going to do that. So don't forget equal signs, limit as x approaches infinity. So square root of x squared plus 1 times square root of x squared plus 1 is x squared plus 1. Minus x times x is x squared. Convenient, right? Over radical x squared plus 1 plus x. Okay, well, let's see. X squared minus x squared. Those are gone. So limit as x approaches infinity of 1 over radical x squared plus 1 plus x. Okay, so we ask ourselves, do we have a polynomial or rational function? So we have a rational function. Can we plug in infinity? Is it in the domain? Well, let's see. If we air quotes again, if we plug in infinity here and here, both of these values, this gets large and this gets large, right? In other words, and though this is not proper notation, it's just to illustrate what's happening, we get infinity plus infinity. But hold on, remember before we said we could not subtract infinities? Where was it? Oh, right there. We said we cannot subtract infinities, but can you take an infinitely large set and add an infinitely large set to it and have an infinite number of values? The answer is yes. So adding and multiplying infinity is fine. Subtracting and dividing infinity is not fine. All right, so 1 over infinity, in other words, denominator's getting incredibly large. That means this goes to 0. And again, you know, these two things are not really proper mathematical notation. They're just to illustrate the point here. Okay, if you write these on a test, I will understand and you'll still get full credit for that, okay? Because that is showing your work. Okay, so there you go. The limit of that, so this original limit is 0. Okay, definitely an important type of question to understand how to do. All right, another example. I know this section's heavy in examples. All right, so right here they say note, the limit as x approaches negative infinity of e to the x equals 0. All right, and you're like, well, why? Right, well, let's talk about why. Here we go. So we're not even going to do the example just yet. We're going to talk about why this little statement is true up here. All right, so we're taking x to be to approach negative infinity. In other words, x is a negative number, right? So in other words, we've got e to some negative value, which means 1 over e to that x value, right? Okay, and what happens then if this goes to infinity? If x goes to infinity, then e to the x goes to infinity. And if our entire denominator goes to infinity, right, denominator gets huge, fraction gets small, right? So this will approach 0 as we go to infinity or negative infinity. Okay, that's an important concept right there. All right. Okay, so let's do this right here. All right, so evaluate the limit as x approaches 0 from the left of e to the 1 over x power. So this 1 over x is the exponent on e. Okay? All right, so what we need to do here is a substitution first. Okay, so we're going to say let t equal 1 over x. Okay? Since we're changing the variables, and this is a kind of a preview to Calc 2. You'll see this stuff a lot in Calc 2. So let's see. So if t is 1 over x, as x approaches 0 from the left, because that's the limit we're going to be doing here, right? As x approaches 0 from the left, 1 over x is going to approach what? Think about that. Getting super close to 0, but on the negative side. If your denominator is getting incredibly small, the fraction's getting incredibly large. On the negative side means 1 over x is approaching negative infinity. Okay? Well, 1 over x approaches negative infinity. That means t will also approach negative infinity. All right? Okay, so now let's do this problem. So limit as x approaches 0 from the left, e, now instead of 1 over x, we're going to say e to the t, because we made the substitution here. All right, so this equals the limit. Oh, my mistake. We didn't do our substitution yet. There we go. E to the 1 over x. We're still in x's here. So then the limit as t approaches negative infinity of e to the t. Now we made our substitution. All right, this is going to be 0 because of that property up there. Okay, because t is going to be a very large negative number. That means it's 1 over that e to a very large negative exponent, which means the fraction goes to 0. Okay, so again, you're seeing how we have to keep manipulating these problems to make them work for us. They don't work for us in the beginning usually. We have to figure them out. We have to manipulate them. All right, another one here. Ooh, trig. Everyone loves trig, right? Well, I do. But I'm a math teacher. I guess I should. Example 6. Evaluate the limit as x approaches infinity of sine of x. So you're probably thinking, oh, there must be some fancy, crazy, 5-page long algebraic way to do this. Nope. Work smarter, not harder. There's a graph. There's a sine wave. Right? As x approaches infinity, what happens to this sine wave? I know it's not to scale, but it keeps oscillating forever, right? So this limit does not exist. DNE does not exist because it's going to oscillate forever. So if you see a question like this on the exam, draw a little picture. Again, it doesn't have to be to scale. And say, well, this limit does not exist because the function oscillates forever. Okay, in other words, it's never going to reach a specific value. Okay. Example 7. All right, find the limit as x approaches infinity for x cubed and negative infinity for x cubed as well. Again, you're probably thinking, well, some crazy, huge algebraic manipulation. Nope. By now, you should know what an x cubed graph looks like. All right, it's a broken parabola. So you tell me, as we go to negative infinity, what's happening to, on the x-axis, what's happening to the y value? It's going to negative infinity, isn't it? Yep. And as x approaches positive infinity, the y value approaches positive infinity. So there you go. Nice and easy, just a little brain break here, right? Instead of doing all this crazy algebraic stuff, sometimes we just take a break. But this is what I'm showing you is, don't always think it's some crazy, messy, large problem. And there's a hint on tests and quizzes right there. If I only give you a little bit of space like this, the answer should be short, right? In general, if I give you a lot of space, then yeah, it probably means you have to do a lot more writing, okay? Not always, so know your stuff. All right, here's another one. Find the limit as x approaches infinity of x squared minus x. Well, so again, this is a polynomial, right? We're allowed to plug in infinity because everything's in the domain, every real number's in the domain of a polynomial. So again, we're air quote plugging in infinity here and here. All right, so what happens? Well, we get that darn infinity minus infinity again, and remember we said we can't do that. Okay, bummer. All right, so that didn't work. So we've got to algebraically manipulate this thing. So let's see. Limit as x approaches infinity of x squared minus x. Well, let's put some equal signs here. Well, we could factor that, can't we? There's an x in common here and here. Okay, let's factor out an x. So if we factor out an x, it means divide each term by an x. We get x minus 1, correct? Okay. If you don't believe me, you can redistribute that x outside into the parentheses and you'll see you'll get it. All right, so now again, let's air quote plug in infinity. Oops. Here and here. Okay. So x obviously goes to infinity. And x minus 1, well, infinity minus 1 is still infinity, right? Oops. So this is times infinity. But remember we said before, we're allowed to multiply infinity. A large number times a large number is a large number, right? So this limit is infinity. Pretty cool, huh? Okay. Moving on, another one, example 8 again. See, I have so much fun with 8. There, change that to a 9. Oh, whatever, doesn't matter. All right, so find the limit as x approaches infinity of x squared plus x over 3 minus x. We cannot just plug in infinity, right? Because we'd get infinity over negative infinity, and infinity over infinity doesn't work. So we've got to use that trick where we find the variable in the denominator with the highest exponent, in this case just plain old x. We're going to divide every term, right? So there's 4 terms here. Divide every term by x. All right, and show your work. Limit as x approaches infinity. Okay, let's simplify. Limit as x approaches infinity. That'll be x plus 1 over, so what happens to 3 over x as x goes to infinity? As x gets huge, that fraction becomes incredibly small, right? It goes to 0. X over x is 1. All right. So this really becomes the limit as x approaches infinity of x plus 1. Well, if we air quote plug in, well, because we have a polynomial, we're allowed to plug in infinity plus 1 is infinity. Okay. All right. And there we go. All right, moving on. Precise definitions sounds fun. So we skipped section 2.4 for a reason. That's something called epsilon delta proofs. You will do those later on in life, and they will be horrible and painful, but actually quite interesting, to be honest with you. So yeah, if from this point on in these notes, I'm not going to cover the rest of this. You're welcome to read it. Don't worry if you don't understand it, because you'll learn a little bit more about it in Calc 2, more about it in Calc 3, and then you'll do it in depth if you go on to real analysis, which is basically Calculus 4. Okay? Yes, there's more calculus out there. All right, thank you very much.